Hello, everyone. Delighted to have the opportunity to present our research at this oral session. I am here to introduce a fast online omnidirectional quadruped jumping framework via virtual model control and minimum jerk trajectory generation. Some quadruped animals can jump rapidly and aggressively to avoid dangers when situated in unfamiliar environments. As you can see in the video, when a cucumber occurs suddenly, the cats immediately perform fast and powerful jumping. Robots aiming to avoid unknown obstacles must perform omnidirectional jumping promptly, which requires fast, skillful planning and dynamic execution motions. Various experimental conductions demonstrate the great potential of optimal control to provoke robots to achieve robust jumping motions. Robots can perform remarkable jumping motions and navigate in the local environment. Optimization-based methods can be divided into offline and online. The offline omnidirectional jumping trajectory optimization methods often require a robot to be prepared in a quasi-static state and cannot perform jumping consecutively, and the online omnidirectional jumping trajectory optimization methods are confined to real-time limitations. As for our previous work, based on the evolutionary algorithm, the trajectory generator is sometimes not reliable in extreme cases, and the local minimum and the solving failure also confines the possibility for robots to perform rapid jumping. In our work, enabling quadruped robots to perform omnidirectional jumping consecutively, we proposed a framework that minimizes the computing time of the trajectory planner and the reference tracking controller to improve the agility of quadruped robots significantly. Due to analytic solutions, the minimum jerk trajectory planner efficiently generates a center of mass reference path in the jumping phase with numerical stability and dynamic compatibility. Aiming to track reference motions, an intuitive virtual model controller is deployed to compute the force of feet with low computational resources. Then, in the landing phase, a whole-body controller guarantees the center of mass inside the support polygon of 4 feet, ensuring the stability and compatibility of the robot's body. The whole process is computed on Intel i3-8145U and consumes within 50 microseconds, revealing the remarkable real-time performance of the framework. The framework's efficacy is verified on open-source Mini-Cheetah, and the robot generates multiple reference centers of mass trajectories and performs omnidirectional jumping behaviors consecutively. As mentioned above, our framework is divided into 3 parts: the minimum jerk center of mass trajectory generator, a VMC tracking controller, and a passive whole-body landing controller. Given the desired XYZ coordinate with respect to the inertial frame, a smooth trajectory for the quadruped robot's jumping motion is generated by a minimum jerk generator. First, to make a quadruped robot well track the space, the flatness outputs, the polynomial order of the smooth trajectory is selected as 5, and it is convenient to formulate it as 3 piecewise segments. Then we can get the jerk of each segment. Second, the optimization program of figuring out a trajectory equipped with the minimal acceleration reference can be formulated. Through Richter's work, a closed-loop form of the optimization problem can be written and get the analytic solution of this problem. Finally, we get the minimum jerk trajectory of the center of mass in analytic forms. The next step is generating motor torques to track the center of mass reference trajectory generated by minimum jerk in the jumping phase. The virtual components producing virtual forces do not exist in the real world. Choose spring and damper as the robot's virtual components, then we can get the center of mass's reference acceleration and angular acceleration. The rigid body dynamics are written as listed, and an optimization program can be formed. The constraint is the friction cone constraint. Finally, the motor torques can be computed by the law. The quadruped robot leaves the jumping phase and enters the flight phase. As for the landing phase, we implement Schamel's passive WBC controller to ensure a safe landing at the end of the flight phase. The whole algorithm is listed on the right side of the slide. The whole algorithm would not cost more than 50 microseconds on Intel i3-8145U. The results are the open-source Mini-Cheetah is able to perform consecutively omnidirectional jumping, including the front jump, the front left jump, rear right jump. Here are the figures of torques and positions of motors when robots perform the whole omnidirectional jumping. You can clearly see the start of the jumping phase, flight phase, and landing phase. The whole process of jumping lasts about 0.6 seconds, and the start of the landing phase is pre-planned in the passive WBC landing controllers. To demonstrate better the simple but effective omnidirectional jumping framework, we supplement our experiments on the Xiaomi CyberDog because the aging motor coils on open-source Mini Cheetah confine the performance of the algorithms. The first video illustrates the CyberDog's ability to perform aggressive jumping. The CyberDog is able to jump 67 centimeters long and about 20 centimeters maximum height, whose total length is about 55 centimeters. The second and third video demonstrates the capability of CyberDogs to perform omnidirectional jumping. In conclusion, our work proposed a real-time omnidirectional jumping framework for quadruped robots. On the one hand, this framework consumes at most 50 microseconds on a low-cost computer. On the other hand, the algorithm is very simple but effective, enabling the CyberDog to perform rapid and impressive jumping. There's one thing to address. Sometimes the passive whole-body controller does not work, resulting in the failure of landing. Our next focus will be developing a new landing controller that effectively manages horizontal and vertical speeds to preserve landing posture.